Well, good day, everyone. I'm not sure what time of the day it is where you live, but whatever it is, I hope you've had a great day so far and more to come if it's an early morning for you. Today, we're going to talk about predicting useful life with an FMEDA. Now, this webinar is part of our spring 2023 FMEDA webinar series. Created because we've had a lot of questions about what is this FMEDA and what do you do with it, and would you please teach some of us how to do it? And we're going to. People at Exida were the inventors of the FMEDA, and we very much wish to share our knowledge. This webinar is on predicting useful life, as I said, and it's something that we did not think of when FMEDAs were first created back in the late 80s, early 90s. But it can be done, and we had some incentive to do it because functional safety standards specifically require that it be published. So my name is Bill Goebel. I work for Exida. Exida is an international knowledge company, we like to call ourselves. We have a certification group, an engineering tools group, and a service group. We're talking today from the software tools group. That tools group has a suite of tools for systems level and for embedded system device product level development work. The tool is used by many of our people at Exida who are in the certification group because we use it to help evaluate and audit the functional safety projects that we are working on, and even our cybersecurity projects. Just to make sure we're in the right context. An FMEDA is failure mode effect and diagnostic analysis. It's a quantitative, detailed approach that predicts failure rates of a device, a product, a system, or a subsystem, whatever the scope of analysis is, based on studying the behavior of all the electronic or mechanical components. It is a bottom-up inductive approach where we look at every component and every failure mode of every component and work up until we get the failure rates, failure modes, and other useful metrics, including proof test coverage. And of course, the reason proof test coverage exists in the FMEDA today is that, as I said, it's required. It's required for good probabilistic analysis, which is done for availability, warranty, and functional safety. Useful life is one of the metrics that can and should be generated as part of an FMEDA. Now, I hope you may very well be very familiar with what the term means, but we're going to talk about it a little bit. But in order to understand useful life, you have to understand failure rate. Now, failure rate's defined as the number of failures per unit operating hours. Many reliability engineers use the lowercase Greek symbol lambda, and common units are called failures per billion hours. It has been shown in many sets of life test data and accelerated life test data that failure rate is not constant. It actually varies as a function of time. But we have found that the math is much simpler. if we assume a constant number based on the average over a time period. And I'll show you on the graph how we do that. One of the concepts that I find very useful, I learned it at Eindhoven University in the Netherlands, is the stress strength. They called it stress susceptibility failure concept. A failure occurs when stress is greater than the associated strength. Now, in fact, strength varies typically because of some manufacturing deviations, or in other words, manufacturing flaws, material defects, and so forth in a batch of produced product. But strength also varies as a function of operating time, and strength varies. It's typically reduced as a function of some stress factors. Did you ever read about integrated circuits and their susceptibility to electrical overstress dropped every time they got hit with a surge or an electrostatic discharge? That's what I'm talking about. We don't have now we could very accurately predict failure rates if we understood all the stress factors in the environment and all the strength variables, but that kind of information is very hard to obtain. Now, if we represent stress and strength with probability distributions, the cumulative probability distribution for strength and 1 minus the cumulative probability, they show an intersection, a convolution. That is where that area is proportional to a failure rate. So think about that concept. You can read a lot about it. There's a lot that's been published, including one of my mentors, Dr. Brombecker at Eindhoven. Part of this concept is that you can design a product to be stronger or, for example, weaker. Let's focus on the positive right now, stronger, and do many different things to the electronic projects or the mechanical projects. And point for the moment, the stronger you make your design, the lower the failure rate and the longer the useful life. Remember that, and we'll show you what I mean by that in just a moment. As the device strength gets stronger, look what happens to the convolution, the overlap area between these two curves. It really drops in a non-linear way. So that gives us some incentive. And if the stress strength increases, you will have a longer useful life because it takes longer for the strength degradation to impact the failure rate. Now, I do remember a series of papers by what appeared to be a very clever guy, Cam Wong. He created the roller coaster curve, and it was a more detailed version. But for the time being, and I really like that model, but for the time being, we'll stick with the old-fashioned bathtub curve. Failure rates theoretically start high, they drop, and they continue to drop during the useful life operating time. But at some point, the failure rate goes up very non-linearly. And if you look at this greenish blue line, that's a simulation that was run by Ewan van Beurden at the university. And I was kind of shocked how rapidly the failure rate went up as a function of strength degradation. You can see why that occurs by simply moving the stress line in the weak direction. You can easily see how the non-linear increase in failure rate occurs very rapidly. Mechanical people call it wear out. the reliability engineering people call it the wear out period. And in general, we have three phases of the bathtub curve. The front end has been called infant mortality. Now, it's definitely my opinion, and I have seen supporting evidence that this part of the curve is disappearing rapidly with the improvement in quality procedures at manufacturers and testing done at manufacturers. So we kind of are rapidly getting to the point where this phase is going to disappear. That leaves us with the normal operating phase and then the wear out phase, which signifies end of the useful life. In functional safety, in reliability engineering, you can see how we gather up failure rate data. Time to fail is the statistical variable. Typically, as soon as a product is released, and we try to gather up as much data as we can in the early phase of a product life. And you can see if we take an average over this period, the constant number that we come up with while gathering data in the early phase of the useful life remains rather conservative for the rest of the usual life as the real failure rate actually keeps declining. So this constant failure rate model is what we use for functional safety and for virtually all reliability engineering tasks, as it vastly simplifies the math. And it's conservative, it's pessimistic. In functional safety, we need to know the useful life, because when the useful life ends is when the failure rate goes way up. When the dangerous failure rate goes up, the risk reduction that we need in a safety system will not be there. Risk reduction factors will actually drop. So it's a real bad idea to run devices that are part of a safety function to failure. 61508 and the process industry functional safety spec 61511 have very clear requirements that the maintenance procedures should be set up to replace or refurbish before the end of the useful life. And that really does make sense for these safety critical systems. Well, if we need to know this variable, and we do, many people spend a lot of time guessing at it, there is a better way. Now, the first thing I want to establish is, do electronic circuits ever have an end of useful life? I know when I started my career, I certainly thought they would last forever. I mean, there's no moving parts. There's no bearings to wear out. There's no, I keep thinking of my engine. There's no piston walls to get scratched up or cylinders to bore. It's just different. There's no moving parts. So why in the world would the electronics ever wear out? I was kind of misled, I guess, by the term wear out. Electronic components do not wear out the way mechanical parts do, but there are mechanisms like electromigration and evaporation, degradation of customers, hardening of the plastics, insulation degradation, and whisker growth between conductors on a printed circuit board. Now, that was real bad news when lead-free solder was introduced, and I know it's a whole lot better today, but I am told by an expert that I talked to earlier this week that it does still exist. What about integrated circuits? The electromigration is one of the wear-out mechanisms that is mentioned in the literature I'm able to find on the internet. It's the gradual movement of ions in conductors. It can eventually short the gate of an FET to the drain or the source, but it doesn't happen very quickly. Obviously, in FETs with a very large gate geometry, like micrometers, it's definitely greater than 50 years. But think about what's happening in the world of the very large scale integrated circuits. I saw a news release from Intel some weeks ago that they have now developed a 3 nanometer gate geometry, so they can get more and more transistors on a piece of silicon. And that has been going on now for decades, of course. You integrated circuit experts recognize that as Moore's law. So I saw a data sheet from a major semiconductor company and a microcontroller, a CPU with lots of peripheral circuitry all on one chip. And it said right in there, useful life, 10 years. And I thought, oh my goodness, 10 years? I mean, that's okay, I guess, if you're designing a cell phone or maybe even a laptop, a consumer product, but a lot of industrial process products are expected to run at least 20 years. I have a sad tale to tell. One of the exida certification customers designed a real nice piece of equipment. They were ready to take it to market, and they were in the process of getting their certification, and we issued a report, an FMEDA report, which indicated useful life of 10 years. The marketing people called up and says, you crazy? This thing has to last 30 years. That's a customer spec. I says, oh, well, I guess all you have to do is replace that microcontroller. And what? The product was withdrawn from the market. The entire development group was shut down. Very bad outcome. I hope this also emphasizes the need to pay attention to useful life in the components we choose. LEDs and optocouplers, you've read about it before, I'll bet, but I know I have. Light declines with operating time. Now that's getting better and better. I know optocouplers used to give you charts of how rapid the degradation occurred as a function of the input current to the LED inside the optocoupler. Capacitors is probably the worst of anything, in the past at least. Go on the internet and search for electrolytic evaporation or wear out of electrolytic capacitors. Some of the most famous wear out problems in the electronic industry occurred because of these capacitors. Now, I will admit they're getting a lot better. The capacitor people are coming up with new chemistry and new designs that are so much better than what we had even 5 years ago. But you do have to watch out. You got to understand the spec and the useful life of your components. Now, how do you calculate, or how do you estimate, or how do you look at useful life of a system? Well, most products have a number of components, and they are all necessary for the system to work. If they weren't necessary, they probably wouldn't have been designed in. A series system in reliability engineering is where all the components must operate for the system to operate. Make sense? Good. So within a repairable unit, The component that has, this is pretty simple. So I'm about to tell you all you need to know. The component with the smallest useful life wins. It dominates. As soon as this component fails, the device fails. So the useful life for this device is 10 years. I mean, you don't get to take an average. Sorry, it doesn't work that way. Worst case wins. What are you going to do about it? Well, I had one engineer suggest, I know what we're going to do about it. We're going to put in a redundant component. All right, are you going to have some switching mechanism while so that only one of them runs at any moment in time? No, that's way too complicated. We'll just put in two of them. All right, let's stop and think. Stop and think. The unit, the repairable unit, was manufactured with all the parts installed at the same time. This repairable unit is under the very similar, if not identical, stress probabilities. The components have virtually identical strength probabilities. And so if we really think about it, component 4A will fail not exactly at the same time, but they will reach useful life at approximately the same time. And we have not improved useful life. Now, redundancy will have a significant impact on the failure rate caused by this pair of components, but you have to be careful. Redundancy is often an expensive, a solution that costs more than is worth. So how do we know the useful life of our components? Well, you're going to have to get that information. Many components today will give you a specification right in the component data sheet. We do need to remember, though, the stress strength concept and the fact that the failure rate and the useful life are a function of stress versus strength. Let's take a look at this silicon carbide FET. Now, these are big, high current FETs. They're meant to handle many, many amps of current. Some of them are physically quite large, as big as my coffee mug, or even bigger, perhaps. Let's take a look at the useful life specifications. I see right away that the useful life is a function of stress. If I'm going to operate this thing at 20, 40, or 60 degrees C, I'm going to get a 20-year useful life. But if I'm going to run it at a much higher stress level, the useful life drops to 10 years. Whoa, that's pretty bad. Maybe something like that is what happened to that microcontroller chip we were looking at. Well, all right, the data shows useful life decreases with higher stress levels. Useful life increases with higher strength. What about environmental stress? Well, even if we're operating at a high 80 or 100 degrees, we're going to get different useful life in some operating profiles. Now, what I mean by an operating profile is the environmental parameters. And let's take a look at profile number 4. What is profile number 4 is sub C. That's where your equipment is underwater. The really nice thing about that is that you have a really good heat sink compared to air. Water is much better at cooling. So the useful life goes up in that environment. Useful life changes with stress versus strength. You can also do things like pick a better component. Let's take a look at an electrolytic capacitor called 105/2000. The 105/2000 capacitor is much less expensive, and the ones I looked at are actually a little smaller. What is it? In profile number 1, 5 years? Oh my. Well, again, I'm not sure that would be a problem in a consumer product, although I'd be kind of annoyed if I keep my laptops longer than that, but many do not. So maybe you could get away with that capacitor in some environments, but not in an industrial process environment, not in many critical applications. Let's compare that to one that's marked 125C/ let me look, 2,000 hours. Yeah. Whoa, nice. 20 years. That's what I should be using. I don't care if it takes up more space or it costs more. We've got to meet our useful life specification, a minimum of 20 years. So often we can increase the strength and achieve longer useful life. Well, you should understand what useful life is by now. You should understand why we need it. And you should understand the concept of useful life as increases with a design strength. It decreases with increased stress. How do we do a spreadsheet in an FMEDA for this? Well, the idea is so simple. I hope you forgive me. We add a column in the spreadsheet for useful life. For every component, we enter the useful life in whatever, sometimes it's cycles for mechanical, sometimes it's years, or sometimes it's both. And you know the rule, minimum wins. So you just use the min function in the spreadsheet and up pops the useful life. Now you can scan down through your spreadsheet and see where the problem is. And this particular design I was looking at, the 10 years was limited by some very high brightness LEDs. All right, we might be able to drop the current a little bit. I'm going to go pull out the degradation, the useful life degradation chart from the spec sheet, see if I can't get that up. But then we lose the lumens, and there's a minimum lumination spec also. So we're just going to have to do the best to optimize our design. But as you designers know, optimization is what it's all about. Okay, it was trivial. All I had to do was add a column and type a min function. Commercial tools also generate, a good commercial tool would also generate the minimum, the useful life from an FMEDA. I think it's very important. It's an important part of any commercial FMEDA tool you are using. I've always said the embedded component data, the component database for an FMEDA tool is 80 to 90% of the value of any tool. But that database needs to have the useful life in it, as well as the failure rates. Now, I do want to mention briefly that at Exida, we use the OEMX tool suite, and the FMEDA tool I use is called FMEDA-X. So I just want you to know they do exist, and I know that at least this one does give you useful life. So I hope you feel you've got your money's worth. I like to keep these things short and sweet. Although a traditional FMEDA has never looked at useful life, and I know when I started FMEDAs, I wasn't thinking about it either. But it is a perfect place to do a useful life prediction while we're focused on each component in a series system. Failure rates during useful life and the length of the useful life are both impacted by design strength and stress on the component. And by stress, we mean the design stress. How much over-design do you use? How much margin do you use in your component specs? And the environmental stress, primarily average ambient temperature. FMEAs can be done with either spreadsheets or a commercial tool. I personally like to get them done really fast, so I use the commercial tool. The component reliability database, however, to do useful life, the component reliability database must include the useful life data, typically as a function of design stress and environmental stress. I really like any questions you might have. Just so you know, you will get a copy of these slides. A recording of this webinar will be made available. And this is part of the exida 2023 FMEDA webinar series. If you have a question, start typing right now. I'm going to open my question box and look for some. Oh, there's already. How should we manage the uncertainty around component useful life? Generally speaking, we're making a big step forward, even being able to predict it. The component database should predict a pessimistic number, and we're not trying to get down to the precision level where uncertainty is significant. We don't have the data to get down to that level yet. Now it goes on, would we consider each component's distribution? I don't. No, we are not trying to get down to that level of accuracy, and we don't have the data to support that. I'm hoping someday we do. I really would love to see more real data, field failure data gathered. But sadly, I see less and less field failure data being gathered. More and more companies don't even analyze root cause when they get a failed unit back to the field, because it's just so much cheaper to furnish a new unit than to take time troubleshooting or repairing an old unit. I have no doubt some of you have experienced that as well. There's another. What's the difference between useful life and mission time? Oh, that's a good question. It's very confusing. Mission time is how long you're planning on operating a plant or an industrial process. It's the period of time for which we do PFD calculations. Now, useful life is really a completely different variable. You may have devices within your safety function design where the useful life is significantly less than the mission time, in which case your maintenance program should be set up to replace or refurbish while you're within your mission time. You also may have devices where the useful life is much longer than the mission time, in which case you don't have to worry about it. Now, when does a mission time end? Usually when they decide to scrap or stop operating the industrial process. Let me just see if there's more here. What is the useful life? What is the course of action if useful life is less? Repair or refurbish. Often you will stop or shut down, temporarily shut down an industrial process for a brief period of time. In the process industries, I've heard of shutdowns that last a week, sometimes less. And during that time, if your end of useful life will occur before the next shutdown, replace it right then and there. because you don't want to run past the end of useful life because your failure rate goes up and you're not getting the protection levels and the SIL levels you want. Oh, thanks for that question. I'm so glad about that. Bottom line, they are very different. If you have a useful life that's much lower than the mission time, you have to repair, replace during one of your scheduled shutdowns. I hope that was a sufficient answer. Maybe you didn't like to hear it, but that's what we need to do. All right. If you have any more, I haven't seen anything else come up yet. Let me just make sure of that. I don't see anything else on my box. I'll scroll through the whole thing. Uh-oh, there's more. Okay, good. Oh man, my box isn't nearly big enough. How should we manage the uncertainty? Okay, we did that one. What's the difference? Useful life and mission time. Okay, course of action. I think I got them all. Oh, hold it. There's one more here. Would it make sense to have yes, I can get it. I have such a tiny little box. In the spirit of just replace the whole thing, would it make sense to have as close as possible values of useful life in the reliability database? Yes. We try very hard to make them as close as possible, given the data required to justify and support. I will tell you that exida has spent months researching this in 2022, and we spent a few weeks updating in 2023 with the exida component reliability database and made some changes based on all the latest technology. Fortunately, some of the new capacitor chemistries are so much better. We defined those as new components and gave them a conservative but justifiable useful life. I hope that answers your question. Now, what if vendors do not provide useful life information? Well, the first thing I do is go to try another vendor. If I desperately loved the product I was buying and the manufacturer had no useful life, I would search the internet for something similar and make my best guess. But you're going to have to, if you're guessing, you're going to have to make a conservative guess. If you're guessing it's going to be 25 years, back it off to 20 for purposes of your maintenance schedule. And then call the vendor, your favorite vendor, and tell them you really do expect this kind of a thing as they move forward. I've seen many of them start publishing this information as a function of time. If you have any more questions, please don't hesitate to send us an email. We have many white papers, several of them on this subject, and some more detailed webinars on useful life. I thank you all very much for your time. I hope we see you in one of our other FMEDA series webinars coming up soon. Thank you all very much. Have a great day. Goodbye.